Corrosion is simply the oxidation of a metal. So in a drinking water system, typically what we're looking at is the oxidation of iron, lead, copper, or zinc. So your metal itself is in a zero valence state, and that metal is then oxidized to typically a +2 charge. One of the things to recognize is that for these metals, corrosion is thermodynamically favorable in the pipe environment, which means as an environmental engineer, if you're working in distribution systems, you're going to spend essentially the rest of your life trying to fight corrosion and trying to prevent it. So in distribution systems, corrosion is caused predominantly by the presence of oxygen and or chlorine. It's simply, you can simply think of it as rust. In this case, this is a copper pipe, and the copper is oxidized to produce a cupric oxide, and that's the green color that you see here. So the copper is oxidized, something has to be reduced. We'll look at briefly at some of these reactions. In this case, this is a iron pipe. And again, what you see is rust. So that iron has been oxidized to produce a ferric oxide, or in some cases, a ferric hydroxide, depending on how it precipitates. So we can use an electrochemical model of corrosion. As I mentioned, the metallic lead is oxidized. So shown here, we've got a lead pipe. That lead here at PbO, in a zero valence state here. So this would be a zero valence state. And that is oxidized to Pb2+. That releases 2 electrons. Something has to be reduced. In the presence of oxygen, so oxygen is our oxidant, it is reduced from 0 to that oxygen has a -2 charge. So it accepts electrons and is reduced. The oxidation occurs at the anode. The reduction occurs at the cathode. Both reactions have to occur, and there has to be some transfer of electrons in order for this to occur. Now, in 481, Dr. Davies is going to, for those of you in 481, Dr. Davies will spend a lot more time today on this. If you downloaded the notes before last night, you'll see that they're slightly different today, and that's because much of the notes that I had previously, I gave to Dr. Davies. He'll use those today. I will also post his lecture, so you have a little bit more information on the chemistry of corrosion. We're going to focus predominantly today on the engineering. Similar reactions can happen with an iron pipe. So you see here we have an iron pipe. Again, we have the oxidation of iron. It starts out in 0 valence state. It's oxidized to Fe2+. It produces a ferric oxide, releases 2 protons, and as shown here, it is something has to be reduced. It's donating electrons to oxygen. So that oxygen is reduced from O2, which is a valence state of 0, to oxygen in water, which has a oxidation state of 2-. And that occurs at the cathode. And that forms the rust that you saw on that one pipe. Now, we also talk about galvanic corrosion. And here we're looking at a situation where we have two different metals. So they're what we refer to as dissimilar metals, and they're in physical contact with one another. If there is a transfer of electrons, then one can be reduced and one can be oxidized. And you see that here. So in this case, what we have is we have an iron pipe here. We have a copper pipe here. So we have dissimilar metals, and those metals can react. So what happens here is we have oxidation at the anode, we have reduction at the cathode. So copper 2+ is reduced to copper 0, it's essentially plated out, and the iron is oxidized to form this rust. Similarly, if we have a copper pipe connected to a lead pipe, you can see that the lead is oxidized, it's releasing electrons. Those electrons can be donated to copper, and the copper is reduced. So we have a reduction reaction at the cathode and an oxidation at the anode. Often you'll see the term used with active. So in terms of metals being most active or least active. And you can see it in the table here. So magnesium being the most active, if you actually take a piece of magnesium and you throw it in water, you will have a very violent reaction. It is extremely active. Zinc is more active than iron. So that means that if you have zinc, so if we have a zinc and an iron connection, then the zinc will most likely be oxidized, the iron would be reduced. If we have iron and copper, then the iron is the one that is most likely to be oxidized because it's the easier one to oxidize, and the copper would be reduced. So that's what we mean by dissimilar metals. And you can see in these images here, we start out with an aluminum bolt and a copper nut. In this case, we have copper bolt and a steel nut, and we have a steel bolt and a copper nut. And you can see in the case here, it's really obvious. In this one, you see the rust on the steel. Okay. So it's the steel that's being oxidized. Here is a steel bolt and with a copper nut, and you can see the rust right here. So again, you can see the steel being oxidized, and it's a little bit harder to see here, and we've got aluminum and a copper, and it's the aluminum that is being oxidized here. We have a number of indices that we can use to try and assess the level of corrosion that might exist. LSI really is not a corrosion inhibitor. It assesses the degree of saturation with respect to calcium carbonate. So we want to produce water that is neither scale forming nor corrosive. We don't want pipes dissolving. We don't want plumbing fixtures to start dissolve. We don't want metals being released from these fixtures. And these metals can include lead, it can include nickel, chromium, cadmium. These are metals that are produced or used in the production of plumbing materials. So we want a water that will neither dissolve or precipitate calcium. It's also useful to use this to determine if calcium carbonate will precipitate in the filters and the piping network. If we have a significant amount of precipitate, then that can cause significant clogging in the filters and short-circuiting within that filter, or it can cause clogging in the piping network. If we have water that is corrosive, so there the calcium carbonate wants to dissolve, then we have potential corrosion problems in the distribution system. So one of the methods that we use to assess this is referred to as the Langelier saturation index. It is really a measure of the degree to which a water is saturated with respect to calcium carbonate. So we use what is referred to as pHs, so it's the pH saturation, and that is equal to the negative log of the calcium concentration, and we need that in molar units. Okay. Alkalinity, we need in equivalents per liter, and that we'll use in here the negative log of the alkalinity. And then C is an empirical constant that's a function of ionic strength and temperature. You've got a table in your textbook. I have it in here, table 7-5. And that table lists these C values for the various species. Now, if the LSI is less than 1, that means that the water is undersaturated with respect to calcium carbonate, and you would expect that calcium carbonate would dissolve. So that would mean that the calcium carbonate that is precipitated in the pipes that provide a coating on the inside of the pipes prevent the contact of the water with the free metal dissolves. If the LSI is equal to 0, then you're at equilibrium, and if it's greater than 0, you're oversaturated and calcium carbonate will precipitate. With flint, you may have heard lots of talk about the fact that they didn't add a corrosion inhibitor. One of the major problems that's not discussed with flint is the raw Flint River water was oversaturated with respect to calcium carbonate. So, given time, calcium carbonate would precipitate. It would have been calcium carbonate precipitate on the inside of these pipes, along with lead phosphate precipitates, which again prevent or calcium phosphate precipitates, which prevent the contact with the lead metal. The treatment that was used in Flint, which included ferric chloride coagulation and included lime softening, resulted in a treated Flint River water that had a LSI that was significantly negative. And when I mean significantly negative, negative 1.5 and greater. So you have a water that treatment has shifted the equilibrium from oversaturation to undersaturation, and that would have potentially dissolved the calcium carbonate that would have been on the inside of pipes that provided this protective coating. That's something you almost never hear about, but it's something that actually did occur. And it really was a function of the treatment. The Flint River water itself was oversaturated. So let's look at an example. So we have an example here where you're given the characteristics of a treated water. So you're told that this water has a calcium concentration in milligrams, and if these are in milligrams per liter, of 53.65 milligrams per liter, magnesium concentration of 40, a carbonate concentration of 25.2, a bicarbonate concentration of 53.2, a pH of 9.89, and a total dissolved solids of 560 milligrams per liter, and the temperature is 12 degrees C. So we need to be able to take this data here that we're given and put it in a form that allows us to calculate the Langmuir saturation index. We'll need to determine the C value. So since we've got the table here, let's just do that now. So we have a total dissolved solids of 560, and we're told that we have a temperature of 12 degrees. So it's between 2.65 and 2.55. If we interpolate between that, what we find is at 12 degrees, the C value is equal to 2.61. So all I've done is what I did was I drew a straight line between 10 degrees and 20, using this information, determined the equation, and from that determined the C value. So that gives us this C value in the equation here. So for the rest of it, let's just go through, and will give us a review of the unit conversions that we've done and determining alkalinity. So we start with 53.65 milligrams per liter as CaCO3, and this is the calcium concentration. When you're looking at doing these conversions, we did the conversion starting from milligrams per liter as the ion, and we converted to milligrams per liter as calcium carbonate. Essentially, we're working backwards now. So the equivalent weight of calcium carbonate is 50 milligrams per milliequivalent. So we have 1.073 milliequivalents per liter, 1.073 milliequivalents per liter. We have 2 milliequivalents per millimole for calcium, and that gives us 0.5365 millimoles per liter. And we need one last conversion, millimoles per liter, and there are 1,000 millimoles per mole, and that is 5.37 times 10 to the minus 4 molar. What we need to calculate then is P, calcium concentration. So that's the negative log base 10 of our calcium concentration, and that is equal to 3.27. Okay, so that is, we go back here, that is this value right here. Now, we're told that the pH is equal to 9.89. Now, if you recall, we've written the alkalinity expression as equal to the bicarbonate concentration plus the carbonate concentration plus OH minus minus H plus. And I've written this in units of equivalents per liter, milliequivalents per liter, and milligrams per liter as calcium carbonate. So that equation is valid for those units. And for most of the problems we've done so far, in fact, in all the problems we've done so far, we've made an assumption. And we've assumed that the concentrations of carbonate and OH minus and H plus are negligible, and we can simply make the assumption that alkalinity is equal to bicarbonate. We can't make that assumption here because the pH is almost 10. So we're almost to 10.3 is the pKa. That's the concentration where bicarbonate is equal to carbonate. So we need to include both bicarbonate and carbonate in the equilibrium, in the alkalinity expression. So my bicarbonate concentration is equal to 53.2 milligrams per liter as calcium carbonate. Again, we've got 50 milligrams per milli equivalent. I'll do the conversions, okay, all at once. And then we have 10 to the 3 milli equivalents per equivalent, because we need the answer now in equivalents per liter. So that is equal to 1.06 times 10 to the minus 3 equivalents per liter. The carbonate concentration is equal to 25.2 milligrams per liter as calcium carbonate. Again, milligrams, milli equivalent. So we'll divide by 50. 10 to the 3 milli equivalents per equivalent. And that is equal to 5.04 times 10 to the minus 4 equivalents per liter. H plus is equal to 10 to the minus 9.89, and that's molar units. And there is 1 mole per equivalent for H plus. So this is 10 to the minus 9.89 equivalents per liter. And then OH minus is equal to 10 to the minus 14. And I'm not taking into account temperature effects on the equilibrium constant. So ignoring that. And this is 10 to the minus 4.11. So that would be in molar units. We can multiply that by 1 mole per equivalent, and that is 10 to the minus 4.11 equivalents per liter. So the alkalinity is equal to my bicarbonate concentration, 1.06 times 10 to the minus 3, plus 1.04 times 10 to the minus 4. Notice I don't have to multiply that by 2 because I've already done the conversion to equivalents per liter, plus 10 to the minus 4.11 minus 10 to the minus 9.89, and that is equal to 1.646 times 10 to the minus 3 equivalents per liter. My P alkalinity, so the negative log of the alkalinity is equal to 2.784. So my pH sat, as I said, is P Ca2 plus P alkalinity plus C, and that is equal to the 3.27 plus the 2.784 plus C that we calculated previously of 2.61, and that is equal to 8.66. So the LSI is equal to the pH 9.89 minus 8.66, and it's 1.23.
Can't quite see the bottom there where you're writing.
Can you just let me know what you can't see? Because I can see it on my screen, but I want to make sure.
So it's just the very bottom there where you just started writing.
Okay. So we've calculated PCA2 plus, that was 3.27. P alkalinity is 2.784, and C is 2.61. So our pHs, so our saturation pH is 3.27 plus 2.784 plus 2.61, and that is 8.66. The LSI is equal to the pH minus pH sat, so that is equal to 9.89 minus 8.66, and that is equal to 1.23. And that means what? It's oversaturated, exactly. So it's oversaturated, and that would mean that the calcium carbonate would precipitate. Initially, what we're doing is we're going through the conversion. So we start with milligrams per liter as calcium carbonate. We're converting that to milliequivalents, and then we're converting to millimoles because we need the PCA in molar units. Okay, so and then because of the pH, we need to go through and calculate the concentrations of all of the species, and that gives us the alkalinity. So the question is, how does the 1.23 tell us that it's oversaturated? In 481, you talk about Q, the equilibrium constant, or quotient, which is really a function of whether the system's at equilibrium or not. What Langmuir saturation index does is essentially tell us the same information in a different form. So it looks at, what it's looking at is the equilibrium between calcium carbonate, looks at the effective temperature, looks at the effective salinity. So in 481, those of you that have taken 481 or will take 481, there they talk about it in terms of activity. Here, that's incorporated into the LSI equation. So if the LSI is less than 0, that means that it's undersaturated and that calcium carbonate will dissolve. If it's equal to 0, you're at equilibrium. If it's greater than 0, you're oversaturated. And the question is, where did the 2.61 come from? That came from this table here, which is simply a table of C values as a function of temperature and total dissolved solids. Okay. So you can see for a given temperature, as the total dissolved solids increase, so does C. And then as the temperature increases, so if we go, temperature increases, you see that C decreases. So what I did was, we're at 12 degrees. I don't have a value here. I interpolated between these two values and determined the C value to be 2.61. So that's where that 2.61 comes in. So this gives us a sense of, as I mentioned, whether or not that calcium carbonate precipitate in our pipes that protect our pipes from dissolving and corroding will dissolve or continue to precipitate. So it gives us that's what we refer to the stability of the water. We have other measures for corrosivity of water. We'll talk about that later when we talk about corrosion. But LSI really focuses on calcium carbonate equilibrium. So I like to talk about LSI here. The chlorine to sulfate mass ratio is also used, and that's because it appears that chlorine, and this is we're looking at chloride, okay? Chloride can promote corrosion because it promotes the transfer of electrons, and then we have the Larsen-Skold index. So the CSMR is simply the chloride to sulfate mass ratio. It is the concentration of chloride in milligrams per liter divided by the concentration of sulfate in milligrams per liter. And based on an empirical survey of a large number of utilities, what they found was that 100% of utilities that had a CSMR less than 0.58 met this action limit of 15 micrograms of lead per liter. But only 36% met the action limit if their CSMR was greater than 0.58. So it doesn't mean that you will definitely exceed the action limit for lead, but it implies that lead corrosion is more likely to be problematic at a higher CSMR. If your alkalinity is less than 50, then the CMSR should be less than 0.2. Just to give you in Flint, after treatment, the CSMR in Flint ranged from about 2.5 to 3.2. So significant increase in the CSMR. That was because of the ferric chloride that was added, which releases 3 chloride ions for every 1 mole of ferric chloride that's added, or 3 moles of chloride, 3 moles of chloride for every mole of ferric chloride that's added. And then the last index is the Larsen-Skold index, and this was created for mild steel. It, again, is not a perfect index, but it does provide us some indication. And this is the sum of the chloride. Notice your units or equivalents per liter. And basically, it's divided by the alkalinity. And again, the premise here is that the chlorides and sulfates may interfere with the natural passivation, and they help promote electron transfer, which is necessary in order to have corrosion. So the question is, what do I mean by MET? Okay, so this action limit is a treatment technology limit. And the way the lead and copper rule is written is you monitor for lead every 3 years, or more often if you change the system. So you're looking at the concentration of lead in your drinking water in the homes in a particular, it's a set number of samples based on population, and you're sampling the systems that are most likely to have lead. So you're targeting homes with predominantly lead service lines. What you then do, for instance, if you're looking at a large system, you have to sample 100 homes, and it's typically within about a 6-month period. And what you determine is the 90th percentile. So that means that 90% of the samples have a concentration less than or equal to 15 parts per billion of lead. There is no upper limit on that other 10% of the samples. If you meet that, then you meet the regulatory limit and there's no action needed. If you do not meet it, then you have not achieved optimal corrosion control, and then you must work typically with the state agency that has primacy to determine what needs to be done, what modifications in the system need to be done in order to optimize corrosion control. So hopefully that helps in terms of what I mean by meeting the action limit. I know I've gone over, but I think I've only got like one more slide. I'm not going to spend a lot of time. This is just the direct measurements for assessing corrosion. Notice, if you haven't watched yesterday's tutorial, Tom talks about this. In these rigs, they have coupons, and what they're doing is they're looking at weight loss. So they have a rig system set up with coupons in the circulating pipe. They can also look at the pipe itself. They can look at corrosion products to try and assess whether they have corrosion, and they can use various surface techniques to analyze the deposit. So all of this is done to assess corrosion. So I will end here. Happy to stay on and answer any questions about distribution systems. Otherwise, I will see you on Friday. After 481, I will, and I get Dr. Davies' lecture from 481 today, I will also post that and the link to that. So you'll have more chemistry, the more chemistry aspect of corrosion than what I've covered here. So thank you.